Hello, students. This is Dr. Nisha Raj from Government College, Burwala, Panchkula. Topic of today's lecture is semiconductors. This is the first topic of Class BSc 1, Paper 2 and Unit 1. We will discuss the importance of semiconductors in today's session.
You may ask, why semiconductors? Students, today we have turned our face from offline teaching methods to online teaching platforms. And the online teaching platforms require the electronic devices. As I am creating this video using my laptop computer, my electronic gadget, you would also need to watch these videos to grasp this e-content, to learn semiconductors, the mobile, laptop, computer, which may be available to you. And these electronic devices have a key ingredient of semiconductors. I will show you. And this is why that semiconductors are utmost important to understand. So let us move ahead to learn the semiconducting materials. Okay, before taking to semiconducting materials directly, I would like to show you a few electrical appliances that you must have seen at your homes. In this video lecture, I will try to explain the things two times, one in English and then in Hindi, so that all the students watching this video feel convenient and the content is understandable to them. So students, these are the electrical appliances that you must have encountered in your daily life. This radio, TV, mobile, laptop, digital camera, smartwatches. These are the common electrical devices that you must have dealt with. But I just want to ask you a question. Have you ever tried to look inside these applications? Have you ever been curious to see, to find out what are these electrical appliances made up of? So then they are doing such a magical things for you. क्या कभी ऐसी कोशिश की है कि इनके अंदर झांका जाए कि ये ऐसी किस चीज से बनी है कि आप जो कहते हो ये वही करते हैं? And if you have tried to do so, you must have seen various resistors, capacitors, transistors, transformers, ICs, capacitors, and semiconducting materials. So this is the reason that semiconductors are so much significant to understand. So let us begin. There are three types of material if we categorize on the basis of their conduction properties. Number one, conductors. Number two, insulators. And number three, semiconductors. Let us discuss them briefly one by one. So first, conductors. As the name suggests, conductors conduct. Mean conductors are those materials which allow electricity to pass through them. कंडक्टर्स वो हैं जो इलेक्ट्रिसिटी को अपने अंदर से पास होने देते हैं, जैसे सिल्वर, कॉपर, एल्यूमिनियम. Next comes insulators. You're right. Insulators are opposite to conductors. Insulators are bad conductors of electricity. इंसुलेटर वो मटेरियल है जो इलेक्ट्रिसिटी को अपने अंदर से पास नहीं होने देते. Few examples of insulators are rubber, quartz, glass, like this. Okay, have you ever noticed one thing? The electrical wires at our home are consisting of a central core. उनके अंदर एक सेंटर में कोर होती है which is made up of conducting material. Why conducting material? Because conducting material, if we use conducting material, it will allow the electricity to pass through. It provides a path to the electricity to pass through. And this core, this central core, is further covered with some insulating material. Why this insulating material? Why we cover? Because this cover provides us the protection against the short circuits and other possible similar electrical accidents. So this cover is very important. Now third category comes the semiconductors. Semiconductors have some electrical conduction at room temperature. Mean they have electrical conductivity, but this electrical conductivity is much lesser than the conductors. But at the same time, this conductivity is much higher than the insulators. Silicon, germanium, these are the examples of semiconductors. I show you some standard data of few materials. Here in this list, first three elements, copper, silver, aluminium, these are conductors. Next two, glass and rubber, these are insulators. And last two, silicon and germanium, are the semiconductors. Now see, in this table, the second column is of conductivity and there is an adjoining column with the head resistivity is also there. अब ये resistivity क्या है? You may guess resistivity is opposite to conductivity. Yes, you are right. It is opposite to conductivity. जितनी ज़्यादा conductivity होगी उतनी ही कम resistivity होगी and vice versa. अब conductivity क्या है? Conductivity कहाँ से आई? Conductivity originates from the term conduction. And what does conduction mean? Conduction क्या है? Conduction is the flow of current. From where the current originates? Current originates from the flow of electrons. When do the electrons flow? Electron कब flow करेंगे? जब electron atoms से free होकर lattice में motion करने के लिए free होंगे. You know, all the electrons are bound to the atoms. अगर उन्हें लैटिस में फ्री घूमना है, अगर उन्हें करंट को कंट्रीब्यूट करना है, ऑब्वियसली दे हैव टू लीव their parent atom and become free to mobilize in the lattice. So this becomes the reason for current and further for conduction. See, metals are conductors. Metals are already conductors. Why? Because in the metals, the current, since the current is caused by the free electrons, and in the metals at room temperature, already there are very large number of free electrons moving in the lattice. So we need not to provide extra energy or we need not to raise the temperature of the metals for the electrons to make free. But there is one important thing to see. When we raise temperature of any metal, then it should increase conductivity in the metals. But actually it does not happen. Why it doesn't happen? The rise in temperature only causes the rise in resistivity in the metals. It is contrary to our belief. You can compare this with the situation that like there is a huge crowd in any market. Okay, एक बहुत भीड़ है किसी market में and the noise of a gunshot bullet, suppose, then what would it result into? It will result into a serious people stampede rather than their well behaved escape from the market. होता क्या है जनरली, अगर कुछ इस तरह से एकदम से कहीं से गोली की आवाज आए तो भगदड़ मचती है बजाय कि किसी एक सुलझे तरीके से लोग बाहर निकले. The same situation happens in metals. Electrons create hindrance among them on raising temperature rather than a streamlined flow of electrons. But the situation is quite opposite in semiconductors because the semiconductor have considerably lower number of free electrons than in metals. And I tell you now the very exciting part of semiconductors. The conductivity of semiconductor can be enhanced to the desired level. It can be increased up to the desired level, but how it can be done? It can be done using a process, and this process is called the doping. What is doping? Doping is adding small amount of a different material into our semiconducting material, and this different material is called the foreign element or the impurity atoms. Why impurity? Because the other element do not match with our material of concern. That's why these are called the impurity atoms. And by controlling this amount of impurity, we can control the conductivity in the semiconductor. Now, before explaining that into detail, let me revise you the structure of an atom. Students, the most fundamental unit in this universe is the atom. By the way, let me tell you, this fundamental unit is actually the quark, but at this stage, I will not go beyond the scope, and you just make understand it that this fundamental unit is the atom only. Okay, this is the simplified atomic structure of a carbon atom. In the center, the red and blue circles represents the protons and neutrons. And these protons and neutrons reside inside the nucleus. These small black balls are the electrons. The electrons revolve around the nucleus. The total number of protons gives us the atomic number of any atom, while the total number of protons and neutrons gives us the mass number of the atom. Now see, not all the electrons make round in the single orbit. Every electron has its own place. These are different orbits with different energy levels, and each isolated atom has only a certain number of orbits available. These available orbits represents the energy levels of electrons in the atom. As you all know and have learned in your 12th standard, that there is a limit that any orbit can hold this much of maximum electrons into it. And if we talk of, for example, valence shell or outermost orbit, it cannot contain or accommodate more than 8 electrons into it. And these electrons in the outermost orbit or valence orbit is called the valence electrons. I have also shown here the electronic configuration of silicon and germanium. In the valence shell of silicon, say we have third, the total number of valence electrons are 4. And similarly in the germanium, the total number of valence electrons in the valence fourth shell is the 4. See, this is a simple demonstration of energy levels. In the left part, the electrons or the orbits are shown as circular, while on the right it has shown as different levels in the increasing order towards upward. यह एक बहुत simplified तरीका है levels को दिखाने का. The energies of levels are generally measured in the units of electron volts. These are the permissible energy levels numbered as 1, 2, 3 and so on. And there are corresponding energy levels shown on the right part. This right part is actually drawn just for simplicity and for quick understanding. Look, in any atom, as we go far from the nucleus, the energy of the orbit increases. The electron, which lies close to the nucleus, say in the first shell, is tightly bound to it and possesses a small amount of energy. On the other hand, if the orbit is lying far from the nucleus, then the electron in the outermost orbit is lesser bound to it and has greater energy. Whenever you supply energy to the atom through heat, or light or whatever external energy source, electrons gain energy and jump to the higher energy level orbit. Why? Because the orbit in which they were earlier lying cannot have an electron with larger energy. इलेक्ट्रॉन एनर्जी गेन करके हायर एनर्जी लेवल में चला जाता है, क्योंकि एनर्जी गेन करने के बाद वह ऑर्बिट जो कि स्मॉलर एनर्जी इलेक्ट्रॉन्स को अकोमोडेट कर सकती थी, अब हायर एनर्जी इलेक्ट्रॉन को अकोमोडेट नहीं कर पाती। उसकी एनर्जी के कॉरस्पॉन्डिंग जो ऑर्बिट है वो बाहर की तरफ है, इसलिए इलेक्ट्रॉन को बाहर की ऑर्बिट की तरफ जंप करना पड़ता है। And the electron can return back to its original orbit, but only by releasing the extra energy. पहले उसे अपनी एक्स्ट्रा गेन्ड एनर्जी को रिलीज करना पड़ता है, तभी वो अपनी पुरानी ऑर्बिट में वापस आ सकता है। Dear students, see carefully here. Just for our convenience and understanding, we have created this model to simplify the things. When atoms form a solid, many of them have to join together. Obviously, when such a large number of atoms join together, the electronic structure will definitely influence each other. It can never be the same as they had in their individual identity. These electron orbit structure or configuration definitely gets modified in the solids. So this is the picture of a modified situation. See, there are millions of atoms that belongs to the first shell. क्या होता है, जब एक सॉलिड बनता है तो बहुत सारे एटम्स पास आते हैं। अब बहुत सारे एटम्स हैं तो बहुत सारे इलेक्ट्रॉन्स हैं, और ऐसे बहुत से इलेक्ट्रॉन्स ऐसे हैं जो जिनकी एनर्जी फर्स्ट बैंड से मैच करती है, तो वो सब मिलकर फर्स्ट बैंड बना लेते हैं। The first band contains all those electrons which have energy equal to the first shell. Similarly, there would be millions of other electrons which have energy matching with the second energy level, and all those electrons join together to form the second band. Similarly, the third band is created, and for let us say, let us take the example of silicon atom. Then this third band becomes the valence band, as I show you back. In the silicon electronic configuration, third orbit is the valence orbit. So, taking example of silicon, I have written the third band as valence band, and now the fourth band is the conduction band. This is very important to understand here. Conduction band contains all those electrons which are responsible for conduction. It means conduction band contains all the free electrons which will contribute to flow of current, which will be responsible for conduction. So for conduction, we need to make the electrons of valence band to jump to the conduction band, so then the material becomes a conductor. And for this jump, we have to provide extra energy required by the electrons lying in the valence band to reach to the conduction band. This energy can be supplied in whatever mode which is feasible according to the situation. Now, by this time, it is clear to you students that we, by supplying the extra energy, convert valence electrons into the conduction electrons. At this stage, I think I should tell you the energy band situation in metals, insulators, and semiconductors. Here, see, there are the three situations shown here. First are that of metals, or you can say conductors. Second is of insulators, and third is of semiconductors. In the metals, you see, there are already large number of free electrons. Obviously, free electrons contribute to conduction. Then those free electrons are already lying in the conduction band. अगर metals में पहले से ही बहुत सारे फ्री इलेक्ट्रॉन्स हैं, तो इसका मतलब ये है कि वो फ्री इलेक्ट्रॉन्स पहले से ही कंडक्शन बैंड में हैं। उनको वैलेंस बैंड से कंडक्शन बैंड में जाने के लिए कोई एक्स्ट्रा एनर्जी नहीं चाहिए। इसीलिए यहाँ पे देखिए, यहाँ पे जो वैलेंस बैंड और कंडक्शन बैंड है, दे आर ऑलरेडी ओवरलैप्ड। मतलब कुछ इलेक्ट्रॉन्स ऐसे हैं जो कॉमनली लाई करते हैं बोथ इन द वैलेंस बैंड एंड इन कंडक्शन बैंड, so they themselves move into conduction band and conduct electricity, and this is the reason why metals are called the good conductors. Next situation is of insulators. In insulators, this energy gap is quite high. It is of the order of 6 electron volts shown here, and practically it is impossible to cover this gap for the electrons lying in the valence band. Yes, you can say that at very, very high energy or very stressed condition you may take, that electrons can be made to jump to conduction band. But in that situation, insulator would be called as in breakdown condition. The lattice will be ruptured. So normally we can say that this cover is not covered, and the valence band electrons cannot jump into conduction band, and the material of insulator cannot conduct. Now third comes our area of interest, that is semiconductors. In semiconductors, there is a gap between valence band and conduction band, but this gap is considerably lesser than the insulators. सेमीकंडक्टर्स में भी वैलेंस बैंड और कंडक्शन बैंड में गैप होता है, पर ये गैप नियरली 1 इलेक्ट्रॉन वोल्ट का होता है, जो कि इलेक्ट्रॉन्स के को बहुत आसान बनाता है कंडक्शन बैंड में पहुंचने के लिए. It is comparatively easier to lift the electrons from valence band to the conduction band. If we provide energy through any source, electrons in the valence band manage to cover this gap and reach the conduction band. And so then the semiconductor becomes capable to conduct electricity at room temperature. I think the picture is very much clear. Now, for the conduction, for the electrical conduction in materials. So let us move ahead to discuss doping. As we have talked earlier about doping process, which is done to enhance the conductivity of any semiconducting material. But before doping, before adding any extra material to the semiconductor material is said to be a pure material, a pure semiconductor, or in other words, the intrinsic semiconductor. After adding impurity, it is no longer an intrinsic semiconductor but becomes an extrinsic semiconductor. Now you would ask, what is the limit to add any impurity into it? Students, we generally add one part in 1 million part of semiconductor. I mean, one part of impurity into 100 million parts of semiconductor, then the semiconductor becomes extrinsic semiconductor. Before reaching this limit, the semiconductor would be called as intrinsic, not extrinsic. Okay, I believe that now we are well equipped to understand the enhanced conduction in semiconductors. As I do not want to make this video very long to be difficult to grasp the content, let us discuss the enhanced conduction in the next video lecture. So please join me in my next lecture. Till then, stay home, stay safe. Thank you.